Welcome to the Explainer. So today we're pulling back the curtain on a component that's at the very heart of pretty much all modern electronics, the capacitor. They are truly the unsung heroes, working away silently inside all your favorite tech. You've definitely heard a line like this in a medical drama, right? That powerful jolt of energy from a defibrillator? Well, that comes from a capacitor. From life-saving devices like that to the flash on your camera, capacitors are all about storing and then releasing energy. And sometimes the results are incredibly dramatic. All right, let's get right into it. We're going to start with the fundamental rules of how you connect them. Then we'll get into a pretty high-stakes, real-world puzzle they solve for big factories. After that, we'll see just how tough these things are. And to wrap it all up, we are going to untangle a really mind-bending energy paradox. Okay, first things first. We've got to understand the two basic ways you can connect capacitors in a circuit. You can either wire them up in parallel, side by side, or in series, one right after the other. And believe me, each way has a totally different effect on the circuit. Now this is where it gets really interesting, because the two methods are polar opposites. When you connect capacitors in parallel, it's just simple addition. The total capacitance goes up. But if you connect them in series, and this is totally counterintuitive, the total capacitance actually goes down. So with a parallel connection, you can think of it like you're literally adding the surface area of the capacitor plates together. And since capacitance is all about that plate area, it makes sense that the total just gets bigger. It's really that straightforward. And here you can see it in action. The diagram on the left shows the principle, right? And then you see it in the real world. Two 40 microfarad capacitors wired up just like that, and the meter reads 80.1. The math works out perfectly. 40 plus 40 is 80. Simple.
But then we get to a series connection, and things get, well, a little weird. The total capacitance drops, which just feels wrong at first. But when you think about what's happening to the electric field inside, it starts to make sense. Even the formula is a dead giveaway that something very different is happening here.
And yep, here's the proof. We take those same two 40 microfarad capacitors, hook them up in series, and what do we get? Just 20 microfarads. That's less than either one of them by itself. So why on earth does that happen?
Well, here's a fantastic way to picture it. Think of a capacitor as a flexible rubber sheet, a dam, inside a water pipe. A more flexible sheet, or higher capacitance, can stretch more, holding back more water. But if you put two of those rubber sheets in the pipe, one after the other, together they act like one single, much stiffer sheet. They just don't move as much, which reduces the overall amount of water you can store. Same idea with electric charge. Okay, so let's take these ideas and see how they apply to a really high-stakes business problem, one that only capacitors can solve. This isn't just theory anymore. We're talking about big money for big industry. And the answer is pretty simple. To avoid getting hit with huge penalties from the electric company for something called poor power factor. Now, power factor is basically a grade on how efficiently you're using electricity. A low score means you're wasting energy and, well, the utility company really doesn't like that. And they let you know they don't like it on your bill. They've got all these complicated rate structures and penalty charges for being inefficient. It can get super complex, but the bottom line is always the same. It costs you a lot of money. So, factories install these huge banks of capacitors to fix that inefficiency and dodge those charges. Here's the catch, though. You can't just slap any old capacitor in there. Sizing the solution is absolutely critical. If you get the calculation wrong, say by using averages instead of really detailed monthly data, you could make an incredibly expensive mistake. And this chart just lays it all bare. Look, a proper month-by-month calculation shows this factory needs about 600 kVAr of correction. That's kilovolt ampere reactive, by the way, just the unit we use. But if you get lazy and use summarized data, your math might tell you that you need over 1,000 kVAr. That means you'd buy a way more expensive capacitor bank than you actually need. Ouch! So if these components are out there managing these huge electrical loads and saving factories a ton of cash, how are they built to handle all that stress? Well, it turns out they're designed from the ground up to be incredibly tough. The safety standards are no joke, for a good reason. The National Electric Code actually requires that all the wiring for capacitor circuits has to be rated for at least 135% of the capacitor's rated current. And that's not some random number, it's because these things are literally expected to handle overloads.
In fact, if you look at the industry standards, the rules say that capacitors have to be built to handle continuous operation way above what it says on the label. They can take more voltage, more current, and more power day in and day out. This makes them some of the most robust, most durable components in the entire electrical system.
And now for the grand finale. This is where our nice, simple, real-world rules get thrown a curveball by a baffling thought experiment that has stumped engineers for decades. It's known as the two-capacitor paradox.
The setup couldn't be simpler. You imagine a perfect, ideal circuit, no resistance, nothing weird, just two identical capacitors. One of them is fully charged up, holding all of the energy in the system, the other one totally empty. Okay, now you close the switch. And just like you'd think, the charge rushes from the full capacitor over to the empty one until they perfectly balance out. Each one now has exactly half the original voltage. So far, so good. Everything seems totally logical. But here's the paradox. This is the part that will make you scratch your head. When you actually calculate the total energy in that final state, using the standard energy formula, exactly half of the energy you started with has just disappeared. It's gone. So where did it go? Well, the secret is that the paradox only really exists because we were dreaming of a perfect, ideal circuit. In the real world, unlike on our neat diagrams, wires have resistance, and that generates heat. That sudden rush of current also creates a magnetic field and radiates electromagnetic energy, basically radio waves. So that missing 50%? It wasn't missing at all. It was just converted into all these other forms of energy.
And that is just a powerful reminder, isn't it? That the neat and tidy rules we learn are often just a simplified model of a reality that's way more complex, a little bit messy, and ultimately a whole lot more fascinating. Thanks for watching.